Hello and welcome to the 44th session of Porous Media Tea Time Talks. It is part of the Interpol Young Academy. With these seminars, we want to give junior researchers, PhDs, postdoc, and early career researchers working on various topics of porous media sciences a chance to present their work to the scientific community worldwide. This is meant to be a complementary platform to the geoscience and geoenergy webinars, which you can find in our future channels, as well as the Interpol conference, which will take place in May this year in Edinburgh. My name is Mohammed Nouraipur from University of Oslo, and here today I am in the studio with my co-organizers, Sarah Perez from UPPA University and Sang Lee from University of Minnesota. Today's first presentation is by Florian Osselin. After graduating from ESPCI in Paris, Florian defended his PhD in Laboratoire Navier in Université Gustave Eiffel before doing postdoc in Warsaw in Poland, Calgary in Canada, and Orléans in France. Florian Osselin is a physical chemist working on multi-scale and multidisciplinary topics, thermo-hydromechanical chemical THMC coupling during water-rock interactions in geological processes. In parallel, he has started a work towards creating a startup for the deployment of orange hydrogen. Today, as you already know, he is going to talk about orange hydrogen, which is quite exciting. Thank you, Florian, for joining us today, and the floor is yours.
Yeah, thank you very much for the introduction. Thank you for the invitation to present my research. So indeed, as mentioned, I will talk to you about hydrogen, and I will start basically to describe the current situation of hydrogen. Hydrogen, as you probably know, is one of the key components of the energy transition. It's considered to be one of the ways to decarbonize large parts of the industry and the transportation system. In 2021, we have been producing and consuming 94 million tons of hydrogen, and the International Energy Agency considers that by 2030 we should be producing 180 million tons to reach the net zero emission scenario, and in 2050 between 400 and 500 million tons should be necessary to reach these net zero emissions. The problem is that today hydrogen is currently produced by steam reforming, which is using hydrocarbons and water at high temperature to produce hydrogen on one hand and CO2 on the other hand. And actually quite a lot of CO2. You have about 10 tons of CO2 per each ton of hydrogen being produced, which amounts to about 3% of the total greenhouse gas emissions. So in the current situation, obviously, hydrogen cannot be used for the energy transition. Now, the alternative, usually you can see in the media and everywhere, is green hydrogen using electrolysis, electricity, to break the water molecule into hydrogen and oxygen. And the problem is that electrolysis requires a lot of energy. Basically, if today we want to be using electrolysis to produce these 94 million tons that were used in 2021, we need more than 2,500 terawatt hours of renewable energy to do that. And actually today in the whole world, there is only 2,900 terawatt hours of renewable electricity available for all applications. And if we want to reach these values by 2030 and by 2050, we'll need to increase a lot the renewable energy productions. And the current trajectories show that we are not on track to do that. Like, there is not a right path today to reach the amount of renewable energy we need to do both electrification of the energy system and production of hydrogen through electrolysis. Second problem of electrolysis is the price. It's between $4 to $6 per kilo of hydrogen, which is about 4 times what the price of hydrogen from steam reforming. So it's economically also not very competitive. Now, there are some alternatives for hydrogen production, and this is one I want to explore with you today. And one of the main routes is natural hydrogen. So natural hydrogen is actually something that's been known for a while, but was always considered as some kind of, let's say, an anecdote. And it turns out it's actually not an anecdote. It's actually quite significant. You have several occasions on Earth where you can see natural molecular hydrogen, gaseous hydrogen venting from the ground to the atmosphere. One example is shown here. It's Mount Chimera in Turkey. It's a 5,000 square meter zone. It's a mountain, and which is releasing in the atmosphere about between 150 and 190 tons of hydrogen per year. And you can see here those flames. Those flames are like permanent flames. Those are actually, you can light them on fire, and then the fire will keep burning because it's a continuous production of this mixture of hydrogen and methane. Another example of it is the hydrothermal vent, which you can find on the seafloor, usually next to the oceanic ridges. And it's venting hot water. You see the plum of hot water in the bottom of the ocean. And in this water, there is actually a lot of hydrogen too. And interestingly, this is related to life. There is a lot of life around those hydrothermal vents, and the origin of life on Earth could be related to these places. That's some theories. So natural hydrogen, there are several ways it's produced, but the major principal way to produce natural hydrogen is from what's called serpentinization and from the oxidation of iron. So basically you have some rocks called peridotite, which are mantle rocks. So they are found in the mantle, but sometimes with tectonic movements, they outcrop and can reach the surface. And when these rocks actually get into contact with water, then the rock will alter and form serpentine, which is another kind of mineral, hydrated mineral, which results from the reaction of peridotite with serpentine. And during that reaction, actually, there is some iron, which is initially present in the initial peridotite, and that iron gets oxidized, so it's iron 2 getting to iron 3, and in the meantime, water H2O is being reduced to H2. So that's how natural hydrogen is mostly produced. And in total, it's estimated that about 20 million tons of hydrogen is escaping from the subsurface to the atmosphere every year. And considering that hydrogen is a very reactive molecule, you can imagine that only a fraction of what's actually produced reaches the atmosphere. So what we can estimate that there is much more than 20 million tons being produced in the surface every year. And another very interesting feature of peridotite is actually it's also not only producing hydrogen when in contact with water, but it can also react with CO2. And when peridotite reacts with CO2, you see the calcium and magnesium part react with the CO2 to produce calcium magnesium carbonates, which is basically solid CO2. And this is what happens. You can see here on that picture, which it's the Sultanate of Oman in Southeast Arabia. And then you see that you have the peridotite formation, and in between you have some lisvanite formation. And lisvanite is basically another word to call carbonated peridotite. So it's a peridotite that has been extensively carbonated and then contains now a lot of CO2. And it's estimated that 99.9% of the total carbon on Earth is actually stored as carbonate through the reaction with silicates, and in particular through the reaction of serpentine, with peridotite. So this is basically what I've been working on these last years is, can we actually make sense of all of that? And can we actually exploit this double reactivity of peridotite for the energy transition? And this is what the idea we've had. And this is what we call orange hydrogen. So that wasn't the title. And the idea is the following. You have a peridotite formation, these rocks that I've described, and in which you can inject from a well water and CO2 together. So the CO2 dissolves in the water, and then you inject it. The CO2 will percolate through the rock and will react with the rock. So hydrogen will be produced by the reduction of water and the oxidation of iron, and the CO2 will be mineralized and be stored as carbonates. And then you just need another well where you'll pump whatever you're injecting out, and then you can extract the hydrogen and commercialize it. So you can work for the energy transition in two ways, by storing CO2 underground and by producing hydrogen. The quantities are very significant. We estimate, according to the amount of peridotite that are accessible through conventional drilling, that we can have about 100,000 years of hydrogen production ahead of us from that technique, and about 1 million years of CO2 sequestration of the anthropic emissions, of the yearly anthropic emissions. And it's very economically robust because economic estimations show that we can reach the $1 per kilo price of hydrogen, which is on par with steam reforming, and which is significantly cheaper than electrolysis. Now, of course, there are some drawbacks, and the main drawbacks is that the whole system is a reactive percolation system, very coupled with multiphysics and multi-scale couplings, and that need to be understood in order to really make it a reality, an industrial reality. And this is what I'm going to show you in this intricate coupling. So something we developed in the lab after we had that idea is what we call proof of concept. The idea was to basically prove at the lab scale that the idea of producing hydrogen and mineralizing CO2 in peridotites was feasible. And to do that, we used this system. So this is a percolation system. You can see here's a picture. The idea is to inject into a core. You have here a picture of a core. It's 0.5 centimeter diameter, a couple of centimeters long. And what we do is that we inject with an injection pump fluid into that core, and we recover it with an outlet pump, which allows us to set up a constant pressure drop for the injection. And by measuring the flow rate, then we can have the continuous permeability over time of the system, and also we can sample the fluid in the outlet pump, so we have the evolution of the chemistry over time. So the rock we used for this experiment is a natural serpentinite. So it's actually not a pristine peridotite. It's a rock that has been already a bit altered. You see there is some half of percent weight, it's serpentine, and it's also been slightly carbonated. 5% weight is aragonite, and aragonite is actually a form of calcium carbonate. So it's a partially serpentinized, partially carbonated rock. And the idea is to use this rock is that actually let's say it's closer to what we would get on the field rather than pristine peridotite. I'm going to show you 3 experiments that I did. 2 experiments with pure sodium chloride and 1 experiment with sodium chloride and sodium bicarbonate. So the first 2 were just to study hydrogen production and separatization, and the last one is to study carbonation of the system on top of separatization. All 3 experiments were done at 280 degrees, and this is basically what we observe. This is a normalized permeability evolution over time, and what you can see that there is a very strong difference between the experiments without CO2 here on top, yellow and darker yellow, and the experiments with CO2 in red. The experiment with CO2, you see that we're losing 5 orders of magnitude of permeability over the course of about 10 days of injection, while the experiments without CO2, we have barely any modification of the permeability over time. And this difference can be seen on pictures by looking at the cores themselves. This is the initial core here, part of it, the top part of the core. And you can see here on that there is like a large open fracture here on that core. And this is what we get after the experiment. So after the experiment, we retrieve the core, we cut it in half, polish it, and then we can look at it. And then you see that this fracture is now filled with a white mineral, which is actually calcite. And this precipitation of calcite can be seen over all ranges of scales. Here you have at the small scale, at 10 micrometer scale, you have precipitation of calcite. At larger scale, 100 scale, micrometer scale, you have also the precipitation of calcite. You have precipitation of calcite over all scales. And in the experiment without CO2, you actually have the opposite. You have dissolution of aragonite, so initial carbonate mineral, and you have the veins that get emptied. So we can relate this precipitation and the evolution of the permeability through the precipitation of calcite and the clogging of the different percolation paths. Now, the question that remains is why is there absolutely no permeability evolution for the case without CO2? Because in the case without CO2, we still have chemistry. We still have the serpentinization process. And the precipitation of serpentine is considered to actually be decreasing the permeability and the porosity because the serpentine is less dense than the minerals it replaces. So the question that's still open is why there absolutely no evolution of permeability here. And it's actually related to the pore size distribution of the system and where chemistry occurs during the reaction. So here is the pore size distribution. You have large fractures above 100 micrometer aperture, small fracture, 10 micrometer aperture, and then the microporosity, which doesn't control any flow. So the main flow path are here, the large fractures and smaller fractures. And so we imagine that if we want to be clogging the system, then we need to precipitate in those large fractures. That's the only way to really decrease fundamentally the permeability of the system. And that's what occurs with calcite. And the reason why calcite can do it is because calcite is fast to precipitate. Since we're injecting in a short core, then the residence time of the fluid in the core is actually very limited. So the idea is that the precipitate, the mineral that's precipitating, if we want it to precipitate in the main percolation path, has to precipitate as fast in a shorter time as that's the residency time, which is why calcite, which is fast to precipitate, can do it in the main percolation path, while serpentine is a slow mineral to precipitate. So serpentine is not fast enough to precipitate in the main percolation path, in the large fractures. And then when you do serpentinization, basically, you're not going to clog, even if you're supposed to decrease porosity, you're not going to decrease permeability, because there will be no precipitation in the larger percolation path, and the precipitation will only be related to the small, slow flow path of the system. So that's a very fundamental difference, which shows there is a coupling between chemistry and hydrodynamics in these kind of situations. Back to hydrogen production. Here on that chart, I put like all the experiments we did for hydrogen production on peridotite. The 3 experiments I mentioned are here. Here's the experiment with CO2. Those 2 are the experiments without CO2. You see that when we upscale to a cubic kilometer per year, we have significant amounts. The orders of magnitude is 1 million tons of hydrogen can be produced per cubic kilometer per year, and the other experiments are batch experiments, which show a very similar story. The idea behind that chart is to show that we have very significant production. Not only we have a large amount that can be produced over in the whole world, but also we can produce it fast enough to meet the needs of the energy transition. And that's about my conclusion. Basically, what I've shown here is that orange hydrogen has a capacity to provide hundreds of thousands of years of hydrogen and millions of years of CO2 sequestration. But for that, we need to solve all these deep, complicated couplings between hydrodynamics, chemistry, mechanics, and so on. We've shown in the lab that it actually works on some conditions, 280 degrees with some composition and of the rock, of the fluid, it does work. But we need to go beyond and really understand the whole system to be able to go into industrial scale, basically. And on a side personal note, I'm actually leaving academia in a couple of months to start my own company on that topic. And well, we hope that soon we'll be providing the world with orange hydrogen. Thank you very much for your attention.
Thank you very much, Florian, for this great talk. It was very insightful. You showed very interesting phenomena with challenging and actual applications. So thanks for that. And congratulations for your new project and for your startup. So if there is any question from the audience, please feel free to write them in the comments. And I will start with one of myself first. You mentioned the fast precipitation of calcite as a way to clog the main percolation path. Do you see some limitation of this in the sense that it may increase the pressure of your overall system? And have you seen such a thing in your experiments?
So we were injecting at constant pressure drops. So what we see actually is the flow rate just goes to 0 after clogging. If we were to inject at constant flow rate, then indeed the inlet pressure will increase. And that's actually why we're controlling the pressure drop and not the flow rate, because we don't want to get too high of an injection pressure. Now, that's what we see in the experiments. In reality, though, it's actually more complicated than that, because in the lab scale, we don't have all the scales. We have only the size of the core as our scale. And in the field, we have up to 100 meters, even kilometer scale. So there are a lot of fractures of different sizes. And it's very hard to tell on the field if it's going to clog through that process, or there will always be percolation path open because of this multi-scale process. So that's something we need to investigate. It's a very interesting multi-scale processes. For example, in Iceland, there have been some project of mineralizing CO2 in basalt, which is same idea of what I'm presenting here, and they don't see any clogging. There is precipitation, but there is no clogging. So probably the idea of multi-scale is the reason why there is no clogging there, but I have clogging in my experiment.
Okay, thank you very much for your answer. So if there is any question from the studio also.
Yes, I would like to ask one question. Do you think, is there any chance to have parallel reactions or parasitic reactions in parallel to the main equation that you think will produce orange hydrogen? Do you think these kind of reactions in the subsurface, especially when you have uncertainty in the thermodynamics, in the reaction kinetics in the subsurface, will lead to complexities for production of orange hydrogen?
Well, they're going to be, yeah, of course, I presented very simplified chemical equation. It's a very complicated chemical systems. Actually, it's from a geoscience point of view, it's not that complicated, but from a chemical point of view, it's a very complicated process. There is lots of interactions, especially something that's not entirely sure yet is how CO2 and hydrogen will interact, because you can sometimes have a reduction of hydrogen of CO2 with hydrogen. So that's something we need to investigate. But generally speaking, the serpentinization chemistry and the carbonation chemistry is pretty well understood and pretty well defined. So there is I don't expect anything surprising to come out from this chemical system.
So in the meantime, we got some questions from the audience. The first one is from Cyprien Soulen. First, he congratulates you, and then you showed that you have large and small fractures in your peridotites. Are they present naturally, or do you need to stimulate the formation beforehand?
Okay, so there are naturally large and small fractures. There are all ranges of fractures naturally. Now, in all, peridotite formation, ultramafic formation are not very permeable. I don't know if you remember, but on the chart I showed, like the permeability was 10 to the minus 15, of course, which is on the lower side, let's say. So there will be probably, if we want to be industrializing the process, there will be some fracturation involved. We'll need to open the permeability of the system before the injection, probably hydraulic fracturation.
Okay, great, thanks. And we have a question from our second speaker. How do you expect to recover hydrogen? There is often no low permeability cap rock around peridotite serpentinized ultramafic bodies.
So it's actually related to the previous question. So the hydrogen at the pressure will be dissolved in the water. So basically, and it will bubble out of the water once we release the pressure. So when we pump, so it will remain as a one-phase flow until we pump everything out, and then the hydrogen will be recovered from the fluid. We don't expect any leakage of the hydrogen to the surface, because basically the peridotite formation is its own cap rock. As I said, it's a low permeability, and since hydrogen will be dissolved into the fluid, then there is little risk of it escaping through unseen pathways. So the pressure, the depth of working is going to be from 500 meter deeps and probably deeper. So those 500 meters will probably be enough as a cap rock itself.
Okay. So is there any other question from the audience or from the studio here? So I don't see them. So thanks a lot again, Florian. And for the audience, I would like to say that you can also contact our speakers directly afterwards if you have any questions on that topic. And I think we can move to the next speaker of the day. So our second speaker is Damien Freitas. He did his PhD in France, in Clermont-Ferrand, and is now a postdoctoral researcher associate at the School of Geosciences in the University of Edinburgh. His research focuses onto the development of high pressure and high temperature experimental apparatus for the realization of in situ measurement at extreme conditions. These characterization techniques encompass geophysical properties and use synchrotron radiation facilities with time-resolved X-ray microtomography and diffractation. Damien investigates more particularly transient reactions, such as dehydration, partial melting, and free rock interactions, intervening at different stages of magmatic, metamorphic, and metasomatic processes. So Damien, please, the floor is yours.
Hi everyone, is the presentation showing? I've seen that it disappeared for a while. Okay, so thank you everyone for being online. Thank you to the organizing team. It's a pleasure to be with you today, and thank you, Florian, for the very nice talk. And it's a very nice introduction of what kind of problems we have with porous media and geology questions. And as I will show you today, I will show you some new type of apparatus dedicated for these time results, so 4D in situ experiments made with synchrotron radiation microtomography for mostly porous systems. So I am a geologist, so mostly work with geological problems, but bear in mind that this can be extrapolated to any kind of other system. I mean, as long as you have a technique that is working, obviously if you want to study ceramics or any kind of engineering material, there is no problem. So I'm presenting first on the behalf on the whole team, microtomography team in Edinburgh, and this apparatus obviously they take years to develop. It's not easy. It's a lot of money as well and development time. And I'm just a part of this project led by our two permanent researchers, Jan and Florian, a bunch of postdoc in which I am, and all former staff and postdoc and PhD students. So what I will do with this presentation, I will be very simple. I will just talk a bit on the necessity of this type of in situ experiments, why we really need them, and what they can bring to us. Then I will showcase three of the North Arsenal apparatus and explain a bit why they have such weird names. And finally, I will try to show you some examples with some of our geological applications, but bear in mind that, yeah, this can be transposed to yours. And I wanted to do this presentation because, I mean, especially for early career scientists, we often come like with a subject with very dedicated and very specific questions, and we don't often have the tools to to answer all the problems we have, all the questions we have. And it's always good to know what people are doing, especially on the development side, in order to plan together. And or will, obviously we spend a lot of time and a lot of dedication to develop this apparatus, but they are there to be used by the community and for the community, and we try to leave them at synchrotron facilities as well. So please reach us if you're interested, if you have a project with that, because obviously we are happy to help. So why do we really need those in situ characterization? Why do I call in situ characterization? Is all the characterization of property, can be physical, can be chemical, of a rock or your samples. Why that's the real conditions you want to explore. So for rocks, it implies pressure and temperature mostly. And why do we need some characterization? Because if you measure something, if you take a rock in your backyard and you just measure the properties at room pressure, room temperature, there's a big chance that they will not be really relevant of the geological problem you are trying to solve. Another thing you can say is that, okay, yeah, we just drill and try to measure those properties when we are at the right condition. It's possible. You can make some wells and boreholes, but these are extremely expensive. And if you want to test, for example, the strength of a rock in the borehole, you need to like drill, put down some very specific instrument, try to break your rock. You will have not much control on what is going on, and all of this will be again very expensive. And the information we'll have is limited anyway. So experiments offer a way to get more data on that size. Same then for we use a lot as geologists geophysical methods, for example, seismic surveys or magnetotelluric surveys, and you get seismic velocities through your formation. But obviously you try to infer the geology from those physical methods, but you need someone telling you, okay, this rock at this property has this type of velocity, at this rock the other type of velocities, in order to refine and calibrate your physical response. It's a bit the same for models. You can model everything you want. At some point, you need to verify if the physics works, and experiments is usually a cheap way verify that. And the benefit of this in situ experiment compared to the classical experiment is that these are not black boxes. So for example, here I put a picture of a piston cylinder that was in Clermont-Ferrand. You just put like a rock sample, you put pressure, temperature, you let it cook for a while, you stop, and you recover your sample, you do thin section, and you do the microstructure analysis with like SEM, microprobe, the traditional apparatus. This is okay, but it's like baking a cake. You have your mixture at the beginning, you put that in the oven, and then you have a nicely puffed cake. Yes, it's delicious, but you don't really know how it formed, what happened in between, and you have very little information of the temporal scale, what is going through time, what is happening first, what is the rate, and all of this, obviously, the goal is to catch that with the in situ characterization. So first you get the parameters at the right condition, and then you get the time dimension. So let's now move on the Norse arsenal. So they all have Norse mythologic names. This is coming from my boss. I think they're already fan of it. And Edinburgh is pretty far north as well. So we have this kind of Nordic connection. And mostly because Mjolnir, as you can see, is the name that comes often. Mjolnir is Thor's hammer. So it's a very good name for a triaxial device that is meant to break rocks. So as you can see, we have started developing that back in the days. I mean, I was not in the team yet, but they started with X-ray transparent oven, flow cells, various designs, and up to the 3 last designs that are now Mjolnir suites that I will present you today. And those things have been working very well, and most of the papers have been either published very recently or they are in press for the last modified version. So let's start with Mjolnir because they all work on the same principle. So once I explain you Mjolnir, you will understand how the others work. So Mjolnir is a very simple little triaxial apparatus. This is about like 30 centimeters tall, 1 or 2 kilo. So it's not very heavy. And basically you have a bottom here, which is an anvil. It's already fixed, attached to the rotary stage of your tomography bench. Here, the synchrotron. So this part is fixed. You have a bottom piston here, which is fixed. You have a sample that you put on top of it, and you have on top of that, the top piston part, which is then dynamic. So basically, you have anvil, sample, hammer. So this part is fixed while this part is moving. What you can see is that the sample is jacketed. So it's protected from the surrounding middle, which we can control the fluid. So it's like a fluid pressure media. So you can apply a confining pressure with a fluid around your sample. And on top of that, you can apply a vertical actual pressure on top of that, which is making these triaxial devices. On top of that, we modify the tools to have access to the pore fluid pressure. So we have pipes in the pistons themselves, so you can really control the fluid, so you can control the chemistry, but also the pressure of the fluids you have in your sample area. And this is not connected to the surrounding because the sample is tightly jacketed. So for Mjolnir, the samples are 3.2 millimeter diameter, 1 centimeter high. So they are pretty small, and you can reach basically 50 MPa confining and pore fluid pressure, 500 MPa differential stress, so enough to break a rock. I mean, most of rocks, not the very high. If you go with a clogite, this will not work, but like most of, like for example, carbonates and works, and also most of silicates as well. And we have also a heating system. So you have here at the top and the bottom of the part of the cell, band heaters that heat the full cell. So here you heat everything, and this is why you cannot heat very high. So we are rating it for less than 200 degrees, but in fact, 150 is already very good. And obviously I didn't mention, but here is like where you have the sample is the pressure vessel, which is in aluminum and the thinnest part, because this is where you send the beam through. So you have to make this part as thin as possible, especially with the metal, in order to pass your beam through and have enough photons to make a nice imaging. So Mjolnir is really dedicated for these rock deformation studies, and also all these kind of low temperature subsurface reactions, everything happening around 100 degrees C, no problem, and it's a very easy, cheap tool to operate, which is making it quite user-friendly and easy to install, which is great. Now I show you storm Mjolnir. So it's, as you can see, the design is a bit similar. So here a picture at Diamond Light Source with Florian and Derek for scale. So storm Mjolnir is a bit same idea, but it's really dedicated for rock deformation and rock mechanics. It looks a bit bigger because it's been designed to work with bigger rocks. I mean, we quite like when we do rock physics to have samples that start looking like proper rocks. So 1 centimeter diameter, 2.5 centimeters height. You can control, as you can see with those fluid lines, the confining pressure up to 50 megapascal, the differential stress, once again, but with much bigger actuators because your samples are bigger, but about the same capacity. We have here this LVDT, which is just basically a distance meter that gives you the axial displacement, so shows you how actually your sample compresses. And as you can see, this design seems a bit weird, especially the bottom part is very large because we inserted in that storm Mjolnir 2 acoustic emission sensors. So one at the top in the piston and one at the bottom through the bottom piston. And this is very useful because once you do like usually classical rock mechanics experiments, you try to break your rock to make some different types of failures. And what we want to study is the location of the different microseismic activity and link that to the deformation process. So with this tool, you can do this, and I will show you some examples where you can really nicely track grain scale with processes with the acoustic emissions. And finally, Mjolnir, which is also looking a bit like storm Mjolnir. But in this one, all the magic is inside. You can't really see it with just pictures. I spent like the last 3 years of my postdoc developing that tool. So obviously you have the cell, but what also I don't want to hide is that you have all the apparatus around it to make it work. You need the high pressure pumps, you need the manifolds, the heating controller, the cooling system, etc., etc. So you see the cell, but you have to think that it's a full logistic as well around it, and you need to have enough space in your lab to fit everything. Mjolnir basically is the same principle. You have the bottom as an anvil, the sample area here in the center, and the dynamic hammer part on the top. It's meant to operate also with larger samples, a bit like storm Mjolnir, 10 millimeter diameter, 20 meter height. And then you have, basically it's a kind of a really improved, beefy version of Mjolnir, where you have 30 MPa confining, pore fluid, differential stress for 100 MPa, but all of this, you can do that up to 300 degrees, which covers a lot of subsurface conditions, and that was the objective for that cell. That cell is really dedicated to measure low grade metamorphic reaction and all this hydrothermal, geothermal reaction, exactly what Florian showed us earlier with for example, like carbonation and serpentinization. Like this rig has been designed for this type of studies. So now let's show you some examples. So we got most of our data at Swiss Light Source and Diamond Light Source, but we've been working at a lot of different synchrotron. So here you have some GIFs of like a time series of a gypsum dehydration around 120 degrees. So at the beginning, you start from like the dark gray gypsum that will quickly dehydrate into basanite, which is the same calcium sulfate, and water. And what you see is that you create a lot of porosity, all these black pores everywhere, and the basanite needles. You change a lot your rock when you do metamorphic reactions, and we're really interested in how this reaction happens and what are the influence of the parameters such as the pressure, such as the temperature, such as the differential stress on that. And as you can see on those GIF, the quality is very, very good. So you can do segmentation and separate each individual grain from each other and start making, for example, time evolution of the different phase through time, as is on the graph here on the right. You can also, if it goes to the next one, it's a bit slow. Yeah, here we go. So once you have segmented data, what we have done with those, so we have made a lot of gypsum experiments. We investigate a lot of parameters, but what I want to show you as an example is that you can start studying the texture of rocks when they dehydrate, and what happens when you completely change the mineralogy in different type of stress states. So these are the ones that are with high differential stress. So axial stress here is the main one. When on this one, for example, you have the main axial stress being radial, and you really see that those rocks developing like a very nice planar fabric, a bit like what we call on the field the schistosity, when those ones are developing more like a lineation-like fabric. So then you can start studying everything from like sample scale to grain scale, and with the time evolution, because obviously this is just one snapshot of it, and you have the full one experiment basically will be a set of different experiments with just a classical in-lab apparatus. And as discussed earlier by Florian, what we are interested most of the time is to know how a porous network evolves, where the fluid is going. So then you can start, once you have fully segmented volumes like this one, you can start doing fluid modeling velocities and modeling the permeability. And here, for example, you can check the pathways of the developed through the rocks, and you can check then at local scale, because you have everything. You have all the 3D information and you have the time evolution, so you can check where is the reaction going faster near my pipes, what is going on, what is the properties, etc., etc. So this is just to showcase what we can do, and there is a lot. Now a bit of examples on storm here. So this is a video of deformation experiments and a failure experiment in storm here. And what you can see is like you see nicely those shear bands, shear failure developing in the rock. So this is a sandstone, a porous sandstone. And obviously with this data, you can segment that and do some digital volume correlation. So then you can get the displacement at grain scale. So for the same video, same volume, you can see here where the displacement is the most important. So obviously on the fracture, but you can see also that on the upper block, you have more displacement. And the same with the acoustic emission in storm here. So you can really start seeing the process, having the bulk response, having the local response, and also locating all the activity that you will do in a normal and you can basically correlate an event with the microtexture, which is what we all dream about as geologists. And finally, my last slide, with here, some fluid rock interaction we've been doing recently. So I've been starting doing some of those carbonation, hydration, weathering, all chemical weathering of different rocks. So for example, this is a porous basalt where we have drilled a pipe through it, put some fluid flow, and obviously scan during and see what the dissolution happening and precipitation, etc., etc. And some more here, gypsum dehydration to anhydrite this time, forming these very large crystals. This is just very new data. I haven't really had time to work on it, but it's working very, very nicely. So yeah, that's it for me. I just wanted to convince you that those new experiments are kind of like the future of geoscience, where we can get all the classical bulk parameters and all the classical grain scale parameters in one type of experiments. And if you're interested, please feel free to contact us. We are really happy to share. So thank you very much.
All right. Thank you, Damien, for a very interesting topic. And I really like how your advisor named the instruments after Nordic myths. They seem truly powerful. And yeah, now it's time for question and answer. So if there's any question from the audience, feel free to type them in the chat. In the meantime, I have one question, a simple question. Can you give us some idea on the spatial resolution and the minimal time interval between the shots?
Yes, that's obviously one of the most important questions. So, so the resolution for the imaging, this is mostly constrained by the synchrotron. And with this apparatus, usually we work with a pixel size, a voxel size of 2.5 microns edge. So that's the globe. You will find that in most of synchrotrons. I would say then you can decrease that with special beamlines, which will not be the classical tomography beamline, where you can really go down to a few hundred nanometers. but you may expect to count for much longer because you have obviously less photons coming on your detector. Then the temporal resolution. So for Mjolnir, which is the smallest one, you can really get a scan almost a scan per second if you want. So you can start being quite fast. With Mjolnir, is more a scan per minute, per few minutes. The thing also, it depends on what you really want, because the samples are quite large and the window of the synchrotron is smaller. So usually the window is about like a 400, 500 micron height. So if you want to have your full sample, you will need to stack the different scans. So for example, for Mjolnir or Storm Mjolnir, it can take 5 to 6 minutes for scanning, from top to bottom. So that will be the indicator. Faster than that is difficult with the current synchrotrons, but the good news is that they're all going on upgrade right now. So we will increase the flux quite importantly in most of synchrotrons. So we can hope getting maybe, I don't know, an order of magnitude.
Wow. One other simple question is if someone from the outside wants to use this instrument, what will be the general protocol or steps required?
Yeah, that's a very good question. So right now, we are working, Edinburgh is making copies of this apparatus, and some of them are left at beamlines. For example, if you go to GC Cars at the Advanced Photon Source in Chicago in the US, they have a copy of Mjolnir. So the cell is already there, and you can write a proposal for the synchrotron as you will write it normally. But obviously, I would advise you to contact one of us just to know exactly what you want to do, because obviously it's experiment. There's always a bit of tricks here and there. So it's nice to get some support. We are really happy to help you for that. For the other tools, for example, Storm Mjolnir, Mjolnir, they are right now, because they are just being finished, they are just with us, but we have also planned to leave them at beamlines. For example, Soleil and TOMCAT, Psyche at Soleil and TOMCAT at Swiss Light Source. Right now, they are not properties of the beamline, so you have to get in touch with us, and then we can build something together. I just want to say to everyone that those experiments, they are quite difficult to do, so you need to really think about it before just say like, oh, I have a weird idea. Like, just carefully, like, do not be too ambitious. Not like, for example, if I say like this is 30 MPa, don't say, can I do 200? No. And those things come also with a bit of cost to operate, so that's something to bear in mind. But once you have the ideas, then you can write a little project, and I'm pretty sure a lot of people are happy to support that. And I think the next round of Excite, the Excite network, for all this tomography, microtexture characterization, they will support this type of analysis. So that's something that everyone, including PhD students, can apply to. So I encourage you to follow up what they are doing, because you may have some times with those tools.
Thank you. I don't think we have a question on the chat or from the studio. So yeah, I think we can conclude our session. Damien, thank you again for presenting your wonderful work. And if anyone else have questions regarding Damien's work, you can send him an email that was shown on his slide. And it's time to advertise our next session, which will be held in March 14th, 15:30 in Central Eastern Time. So we'll have Mohammad Jabad and Andre presenting on the work on the impact of porous microstructure on performance of redox flow batteries, a modeling study, and swelling, erosion, and dissolution in porous media, how to make the perfect coffee, which could be very interesting to all of us. And thank you all of you to join us here today. And if you have any suggestions, comments, please give us the feedback. And also, if you are interested in presenting your own work in this PMTTT platform, please send us an email. We are very happy to accommodate everything. And this is our team making everything possible. And thank you, everyone, for joining here today. And see you all next month.